A star dies and outshines a billion suns. This is the universe's raw power. The moment a stellar furnace becomes a cosmic forge. Across the cosmos, titanic explosions are not just endings. They are the architects of reality, blasts so immense they seed galaxies with the elements of life itself. By the end of this journey, you will hold 25 mind-blowing truths about the universe's most violent events. We will uncover how a single flash can outshine an entire galaxy, and why the gold in your jewelry was born in a cataclysm more violent than you can conceive. What does it feel like to witness the birth of a black hole? That final, blinding flash of a supernova is an energy event almost beyond human comprehension. In a single second, a core-collapse supernova can unleash more light than an entire galaxy. Think about that for a moment. Our Milky Way galaxy is home to hundreds of billions of stars, each a brilliant sun like our own. Yet the death of just one star in one fleeting second can outshine them all combined. This is not a gentle fade. It is a cosmic detonation of staggering violence. The energy released in that cataclysm is so vast, it equals the total amount of energy our sun will produce over its entire 10 billion-year lifetime, all expelled in a single, shattering event. But this explosion is far more than just a spectacular light show. It is the universe's ultimate foundry. Within that unimaginable inferno of heat and pressure, something miraculous happens. Elements are forged. All the iron in our blood, the calcium in our bones, and the oxygen we breathe were cooked inside ancient stars. But the very heaviest elements, the gold in a wedding ring, the silver in a photograph, the uranium that powers reactors, these cannot be made in a star's steady burning heart. They require something more extreme. They are born in the furious chaos of a supernova's blast wave, where atomic nuclei are smashed together with such force they fuse into these dense, precious metals. In its death throes, a star literally seeds the void with the raw materials for new worlds. Every rocky planet, every mountain range, and every living thing is ultimately made from stardust, forged in these most energetic of explosions. This cosmic foundry operates through two distinct, violent pathways. The first is the fate of the truly massive. Any star born with more than about 8 times the mass of our Sun lives a short, brilliant, and ultimately doomed life. It burns through its nuclear fuel at a furious pace, fusing hydrogen into helium, helium into carbon, and so on, building elements like layers of an onion. At its heart, this process creates an iron core, and iron is a cosmic dead end. Fusing iron does not release energy, it consumes it. So when the iron core grows too heavy, the star's central support system suddenly vanishes. In less than a second, gravity wins an absolute victory. The core catastrophically collapses, falling inward at nearly a quarter the speed of light before rebounding in a shockwave of unbelievable force. This is the core collapse supernova, the death scream of a giant, leaving behind either a super-dense neutron star or the ultimate abyss, a black hole. The second pathway is a slower, sneakier theft that ends in total annihilation. Picture a binary system, 2 stars orbiting one another. One is a white dwarf, the Earth-sized, super-dense corpse of a sun-like star. Its companion, perhaps a red giant, begins to swell. The white dwarf's immense gravity starts siphoning material, mostly hydrogen, from its neighbor. This stolen gas piles onto the white dwarf's surface, increasing its mass and pressure. The white dwarf has a strict limit, about 1.4 times the mass of our Sun. If it crosses this threshold, the entire star, from its core to its surface, undergoes a runaway thermonuclear fusion reaction. There is no collapse, no remnant left behind. The entire white dwarf is vaporized in an instant, a titanic flash of light that completely unbinds the star. This is a Type 1, a supernova, a stellar detonation so uniform and bright it serves as a cosmic measuring stick for the vast distances of the universe. These two explosions leave different fingerprints across the cosmos. A core collapse supernova's light fades gradually, marked by specific elemental signatures in its spectrum, like the radioactive nickel it creates. The thermonuclear blast of a white dwarf, however, lacks hydrogen in its light signature and follows a very precise brightening and fading pattern. By reading these light curves and chemical signatures, astronomers can look at the flash of a dying star billions of light years away and know not just how it died, but what kind of star it once was. That stellar corpse left behind can be a beacon for the ages. In the year 1054, a new star appeared in the sky over Earth, so bright it was visible in broad daylight for nearly a month. Chinese and Arab astronomers recorded this guest star, watching it slowly fade from view over 2 years. They had no idea they were witnessing the violent death of a massive star, an event we now call a supernova. Today, we look to that same patch of sky and see not a star, but a beautiful, tangled cloud of gas and dust we call the Crab Nebula. This is the expanding debris from that very explosion, still racing outward at over 3 million miles per hour nearly 1,000 years later. But the true wonder of the crab is not the ghostly glow of its outer shell. It is the furious heart beating within it. At the very center of this cosmic wreckage lies a pulsar, a city-sized sphere of pure neutron matter spinning at an unbelievable rate. This stellar cinder completes 30 full rotations every single second. With each spin, it sweeps a beam of intense radiation across space, much like the blinding beam of a cosmic lighthouse. If that beam points toward Earth, our telescopes detect a pulse of energy, hence the name pulsar. This tiny, spinning remnant is the powerhouse for the entire nebula. The pulsar's fierce magnetic field and relentless spin generate a hurricane of high-energy particles which stream outward at nearly the speed of light. When these particles slam into the surrounding nebula, they cause it to glow fiercely across the entire spectrum, from radio waves to the most powerful gamma rays. The Crab Nebula is not just a silent, expanding cloud. It is a dynamic engine lit from within by the spinning corpse of its progenitor star. This confirms a fundamental cosmic connection. The Crab Pulsar is a neutron star, and its very existence proves that the cataclysmic core collapse supernova observed centuries ago did not leave nothing behind. It forged an object of almost impossible density, a testament to the universe's ability to create breathtaking new phenomena from utter destruction. That spinning neutron star is a silent witness to a death we saw centuries ago. But what if we could witness the very moment a star's heart gives out? On a February night in 1987, astronomers did exactly that. A brilliant new point of light appeared in the Large Magellanic Cloud, a satellite galaxy of our own Milky Way. This was supernova 1987A, the closest observed stellar explosion in nearly 4 centuries. Its light took about 168,000 years to reach us, a journey across an immense void. But something else arrived first. Roughly 3 hours before that first flash of visible light pierced the night sky, 2 specialized detectors buried deep underground, one in Japan and another in the United States, registered a sudden, inexplicable spike. For a fleeting 13 seconds, they were flooded by 24 tiny, ghostly particles called neutrinos. This was the real-time signal from the supernova's core collapse, and it traveled at nearly the speed of light, unimpeded by the outer layers of the dying star. Neutrinos are among the most elusive particles in existence. They have almost no mass, carry no electric charge, and they barely interact with normal matter. Trillions of them are passing through your body every second, coming from the sun and cosmic rays without you ever noticing. They are cosmic ghosts. But in the final, catastrophic instant of a massive star's collapse, the core becomes so unimaginably dense and hot that it produces a staggering flood of these particles. In that single second, a supernova emits more neutrinos than the number of atoms in a billion suns. for supernova 1987A, that ghostly tsunami washed over Earth. Those 24 captured neutrinos were not just a curiosity. They were a direct telegram from the heart of the explosion, confirming a critical prediction of stellar physics. Theorists had long said that neutrinos carry away 99% of a supernova's total energy, acting as the primary coolant for the newborn neutron star. The detection proved it. We were no longer just watching the fireworks from the outside. For the first time in history, we had felt the star's death rattle, the shudder of its collapsing core, hours before the light of that destruction even reached our telescopes. This transformed our understanding. It gave us a new sense, a way to peer directly into the most hidden, violent moments of a stellar death, using particles that slip through the universe like whispers through a wall. Those ghostly neutrinos signaled a star's core collapsing into a neutron star. But for the most massive stars of all, death is not a collapse but a complete and utter demolition. This is the realm of the hypernova, a supernova on steroids, and it is the likely birthplace of the single most powerful explosions in the entire cosmos since the Big Bang itself, gamma-ray burst. If a supernova outshines a galaxy, a gamma-ray burst, or GRB, makes a supernova look like a flickering candle. For a few fleeting seconds, these events release more energy in pure gamma-ray light than our Sun will emit in its entire 10 billion-year lifetime. They are the universe's ultimate flashbang, so brilliant they can be detected from the very edge of the observable universe across distances of over 13 billion light-years. Astronomers categorize these titanic blasts into two distinct families, each with its own catastrophic origin story. The first are the long-duration gamma-ray bursts, which last from 2 seconds to several minutes. These are thought to be the final scream of a star so colossal, perhaps 40 times the mass of our Sun or more, that it does not simply collapse. Its core, under its own immense weight, implodes directly into a black hole. As material swirls into this newborn abyss at near light speed, it forms jets of matter and radiation so focused and powerful they can pierce straight through the star's outer layers. If one of these relativistic jets happens to be pointed directly at Earth, we see it as a long gamma-ray burst, a beacon of total annihilation. This event is so violent it often completely unbinds the star, leaving no neutron star behind, only a black hole and an expanding cloud of ultra-energetic debris. The second-class short-duration gamma-ray bursts are even more bizarre. They last less than 2 seconds, sometimes just a few milliseconds, but their flash is no less intense. Their origin is not a single dying star, but a catastrophic cosmic merger. Picture two ultra-dense stellar corpses, neutron stars, locked in a final, fatal dance. For millions of years, they orbit each other, slowly spiraling inward as they lose energy in the form of gravitational waves. In the last few seconds, they collide. This merger creates a brief, incredibly hot maelstrom that forges vast amounts of heavy elements like gold and platinum in an instant, and it too is believed to birth a black hole, sending out its own pair of deadly focused jets. A short gamma-ray burst is the signature of this ultimate stellar collision. What makes both types truly incomprehensible is their luminosity. At their peak, a gamma-ray burst can outshine every star in every galaxy in the observable universe combined. All that energy is concentrated into a beam of light narrower than a laser pointer, which is the only reason the universe is not constantly blinding us. We only see them when we are looking directly down the barrel of the gun. To witness such an event in our own galaxy, even from a safe distance of thousands of light years, would be a civilization-ending catastrophe. The sheer intensity of radiation could strip away our planet's protective ozone layer for years, triggering a mass extinction. These are not just explosions. They are the universe's most powerful and dangerous searchlights, scanning the darkness, announcing the birth of black holes and the forging of cosmic gold in the same fleeting, devastating instant. The power of a long gamma-ray burst is born from a specific and catastrophic stellar blueprint. This model, known as the collapsar scenario, requires a star of truly monstrous proportions, one born with at least 40 times the mass of our Sun and spinning at a ferocious rate. Its life is spectacularly brief, burning through its nuclear fuel in just a few million years. When such a titan finally exhausts its fuel, its iron core does not have the chance to form a stable neutron star. Instead, under its own crushing weight, it implodes directly and completely into a black hole. But this is not a quiet disappearance, as an immense amount of stellar material, an entire sun's worth of matter, swirls into this newborn singularity. It forms a superheated, magnetized disk of debris spinning at nearly the speed of light. This accretion disk is the true engine of the apocalypse. From the poles of this system along the axis of rotation, the incredible physics at play funnel and accelerate a tiny fraction of this infalling material into a pair of opposing jets. These are not gentle streams of gas. They are ultra-relativistic beams, meaning the matter within them is hurled outward at over 99.9% the speed of light. Charged by the black hole's rotation and intense magnetic fields, these jets act like cosmic blowtorches of pure energy. They must now fight their way out. For the next several seconds or minutes, these focused beams drill relentlessly through the remaining outer layers of the dying star, which are still collapsing inward. It is a race against time and gravity. If the jets are powerful enough to punch completely through the stellar envelope, they break free into interstellar space. There, they interact with surrounding gas, creating the brilliant afterglow we can see for weeks in X-rays and visible light. The entire star is essentially unzipped from the inside out. The critical factor for us as distant observers is geometry. The energy of a long gamma-ray burst is not emitted in all directions like a supernova's expanding sphere. It is concentrated into those two narrow jets, which typically span an angle of only a few degrees. This intense focusing is why the flash is so phenomenally bright. We only witness this event if our solar system happens to lie within the narrow line of sight of one of those jets. It means we are looking directly down the barrel of the most powerful particle accelerator in the universe, witnessing the precise moment a stellar giant becomes a black hole, its death cry channeled into a beam that can be seen across the cosmos. While long gamma-ray bursts announce the birth of a black hole from a single star, the universe has another, even more meticulous method for creating the heaviest elements. This process requires not one cataclysm but two. When the ultra-dense corpses of stars, neutron stars, spiral together in a final embrace, their collision unleashes an explosion of a different color and character entirely, a kilonova. The name itself hints at its scale, meaning an event roughly 1,000 times brighter than a typical nova, though still dimmer than a supernova. But its true significance is not in its raw power but in its profound creative output. For decades, astronomers theorized about where elements heavier than iron, like gold, platinum, and uranium, were manufactured. Supernova could produce some, but the math never fully added up. The universe seemed to hold more gold than those stellar explosions could possibly account for. The kilonova provided the missing answer. When two neutron stars merge, they create a tempest of unimaginable conditions. The collision shreds these incredibly dense objects, ejecting a small but incredibly rich cloud of neutron-rich material into space. Within this hot, expanding debris, a frantic nuclear process takes place, known as the rapid neutron capture process, or R process. Atomic nuclei are bombarded by a dense sea of free neutrons, allowing them to grow massively in size in a matter of seconds, skipping over stable forms to become unstable, heavy elements. These freshly forged atoms are radioactive, and as they rapidly decay, they release energy that heats the expanding cloud, causing it to glow with a distinctive and telltale signature. Unlike the blue-white heat of a supernova, a kilonova shines with a deep crimson red, a direct result of the light being absorbed and re-emitted by these heavy, exotic elements like cesium and tellurium in the ejecta. This red glow is the cosmic fingerprint of gold being born. The confirmation came dramatically in 2017. Gravitational wave observatories detected the ripples in spacetime from two neutron stars merging 130 million light-years away. Just seconds later, space telescopes pinpointed a short gamma-ray burst from the same location. Then, observatories around the world swiveled to look, and they saw it, the evolving red glow of a kilonova. Spectroscopic analysis of that light revealed the unambiguous signatures of heavy elements being synthesized in real time. In that one event, astronomers estimated that the collision forged an amount of gold and platinum equivalent to several hundred times the mass of our entire planet. Every gold ring, every platinum catalyst, every piece of uranium on Earth likely originated in such a violent, beautiful merger of dead stars. The kilonova is more than an explosion. It is the universe's most exquisite jeweler operating in the heart of a cosmic collision. That kilonova glow was not just a prediction waiting to be seen. On August 17, 2017, the universe sent us a message written in 3 different languages. For the first time in human history, we did not just observe a cosmic cataclysm. We experienced it with multiple senses. It began with a faint, almost imperceptible shudder in the fabric of reality itself. The twin detectors of the LIGO Observatory in the United States and their partner Virgo in Italy recorded a distinctive ripple in space-time. This gravitational wave signal, named GW170817, was unlike any heard before. Previous detections had been the deep thuds of merging black holes, events that produced no light. This new signal was higher in pitch and lasted longer, a clear signature of 2 incredibly dense objects spiraling together. The data screamed one thing: neutron stars. Within 2 seconds of this cosmic tremor, NASA's Fermi Gamma Ray Space Telescope was flooded with a short, powerful burst of gamma rays. The timing and the location matched perfectly. The gravitational wave observatories had heard the merger, and Fermi had seen the brilliant flash of the resulting short gamma-ray burst. This single correlation solved a decades-old mystery. It confirmed beyond any doubt that the merger of 2 neutron stars is the engine that powers short gamma-ray bursts. The alert went out to astronomers worldwide. Telescopes across the globe and in space swiveled toward a faint galaxy in the constellation Hydra, 130 million light-years away. What they found in that patch of sky was the final piece of the trilogy. Over the following days, a new point of light emerged and began to change color, shifting from blue to a deep, luminous red. This was the kilonova, the radioactive glow of heavy elements being forged in the merger's aftermath. For the first time, we had witnessed a single celestial event through sound, through light, and through the creation of matter itself. This was the dawn of multi-messenger astronomy. We had heard the space-time ripples of the collision, seen the deadly beam of its gamma-ray burst, and watched the radiant aftermath where cosmic gold was born. One event, observed in 3 completely different ways, gave us a complete picture of a process we had only theorized about. It confirmed that the rapid neutron capture process, the R process, happens in these spectacular mergers, seeding the cosmos with the heaviest elements. That one message from the depths of space did not just tell us how neutron stars die. It showed us how to listen to the universe with entirely new ears. The collision of neutron stars is a precise, brilliant forge, but the universe also builds stars on a scale so vast their deaths defy the very laws that govern them. Beyond the realm of ordinary supernova lie explosions of such monumental violence they rewrite our understanding of stellar limits. We call these events hypernova and pair-instability supernova, and they represent the ultimate expression of a star's self-destruction. A hypernova is essentially a supernova amplified to its extreme conclusion. It is the fate awaiting stars born with more than about 30 times the mass of our Sun. These cosmic titans burn with such ferocious intensity that when their fuel is exhausted, their collapse is not just a collapse, it is a direct and total descent into oblivion. The core does not pause to form a neutron star. It plummets straight through that stage, its gravity so overwhelming it crushes itself instantly into a black hole. This direct implosion channels an even greater fraction of the star's energy into those relativistic jets we discussed, powering the long gamma-ray bursts that can be seen across the universe. A hypernova is the engine of a gamma-ray burst, the stellar catastrophe that lights the match for the universe's most brilliant flash. Yet there exists an even more apocalyptic end for the rarest and most massive stars of all. Imagine a star so colossal, perhaps 150 or 200 times heavier than our Sun. In its final days, the core becomes unimaginably hot. Here, a strange and fatal alchemy begins. The gamma-ray photons that normally provide the outward radiation pressure holding the star up are now so energetic they spontaneously transform. Right in the star's heart, these pure packets of light convert into pairs of electrons and their antimatter counterparts, positrons. This is not a gradual process, it is a runaway reaction. And it spells doom. You see, radiation pressure is critical. It is the outward push that balances the star's immense inward pull of gravity. But when light turns into matter and antimatter, that supporting pressure vanishes almost instantly. It is as if the floor of a building suddenly turned to air. With no outward force to hold it up, the star's core experiences a catastrophic and instantaneous collapse. This triggers a runaway thermonuclear explosion of such ferocity that it does not just blow off the star's outer layers, it completely and utterly unbinds the entire star. Every last bit of the stellar giant is vaporized in a blast of unprecedented power. This is a pair instability supernova. It leaves behind nothing, no neutron star, no black hole, not even a wisp of a dense remnant. The star is entirely erased from existence, its ashes scattered into the void to enrich future generations of stars and planets. These are the true titans of stellar death, explosions so complete they ensure the star that created them can never, ever rise again. But the death of a star does not always leave behind a silent, spinning cinder. Some supernova forge a remnant of unimaginable ferocity, a cosmic entity where magnetism itself becomes a weapon of mass destruction. This is the magnetar, a neutron star born with a magnetic field of almost inconceivable strength. To grasp this scale, consider the Earth's own magnetic field, the force that guides compass needles. A typical neutron star, like the Crab pulsar, possesses a field a trillion times stronger than that. A magnetar's field is a quadrillion times stronger than Earth. This is a level of magnetism so intense it warps the very structure of reality around it. At a distance of 100,000 kilometers, roughly a quarter of the way to the Moon, a magnetar's magnetic field would be strong enough to strip the information from every credit card on Earth. It is a force that can literally tear atoms apart, distorting them into long, thin needles. Magnetars are thought to form when the core of a particularly massive, rapidly spinning star collapses. That rapid spin, combined with turbulent physics in the newborn neutron star's interior, acts like a cosmic dynamo, amplifying the magnetic field to these insane levels. This ferocious magnetism does not just sit there, it actively powers some of the most bizarre and luminous explosions we see. Astronomers believe that the rotational energy of a newborn magnetar, its immense spin, can be dumped into the expanding shell of a supernova blast. By pumping this extra energy into the debris over weeks or months, a magnetar can transform a normal supernova into something far brighter, an ultra-luminous supernova that can outshine its entire host galaxy for an extended period. It is like throwing gasoline on a dying fire, creating a second, sustained explosion from within the heart of the first. Yet the true terror of a magnetar comes from its own instability. These objects are under unimaginable strain. Their crusts, a lattice of iron nuclei 100 trillion times denser than steel, are locked in a perpetual battle with the twisting, titanic magnetic fields trapped beneath. This stress builds until the crust can no longer hold. It fractures. A starquake on a magnetar is a geological event of cosmic proportions. When the crust snaps, it releases pent-up magnetic energy in a cataclysmic flash. In a mere tenth of a second, a single magnetar flare can unleash more energy than our Sun emits in 100,000 years. These bursts of gamma rays and X-rays are so powerful that on December 27, 2004, a magnetar flare from 50,000 light-years away temporarily ionized Earth's upper atmosphere, disrupting radio communications and blinding satellites. It was a stark reminder that we live in a neighborhood where distant, magnetic corpses can reach out and touch us with their fury. The magnetar stands as a testament to the universe's capacity for extremes, a stellar remnant where magnetism is not just a property, but the very engine of its apocalyptic rage. That magnetar's ferocious flare is a unique fingerprint of its violent nature. For astronomers, every stellar explosion leaves a distinct signature written in its light, a cosmic barcode that reveals the identity of the dead star. By carefully recording how a supernova brightens and fades over time, scientists plot what is called a light curve. This simple graph is a treasure map leading to profound truths about the explosion's energy, its ejected material, and the star that created it. The shape of this curve, combined with the specific colors or elements revealed in its spectrum, allows astronomers to sort supernova into fundamental families. We have already met two of the most important. The light from a core collapse supernova from a massive star's implosion tends to rise and fall more gradually. Its spectrum is rich with hydrogen, the primary fuel of the star's outer layers. The thermonuclear blast of a white dwarf, a Type 1 supernova, tells a different story. Its light curve is strikingly uniform. It climbs to a brilliant, sharp peak and then declines in a very predictable, smooth slope. Crucially, its spectrum shows no hydrogen at all, only strong lines of silicon and other intermediate weight elements, the ashes of a runaway fusion reaction. This consistency is not an accident. It is the key to the universe. A Type 1 supernova occurs under a very specific, universal condition. A white dwarf in a binary system accretes matter until it reaches a critical mass limit of about 1.4 times the mass of our Sun. At that precise threshold, the entire star detonates. Because this physical limit is the same everywhere in the cosmos, these explosions always release roughly the same amount of energy and achieve the same intrinsic peak brightness. They are cosmic bombs with identical yields. This makes them perfect standard candles. If you know how bright a light bulb truly is, you can calculate how far away it is by measuring how dim it appears. In the 1990s, two independent teams of astronomers used these celestial light bulbs, Type 1 supernova in extremely distant galaxies, to measure the expansion rate of the universe. They expected to find that the expansion was slowing down over time due to the collective gravity of all matter. The results were shocking. The distant supernova were fainter than they should have been. The only explanation was that these galaxies were farther away than predicted, meaning the expansion of the universe is not slowing, it is speeding up. Some mysterious, repulsive force, now called dark energy, is stretching the very fabric of space itself, accelerating the cosmos apart. That discovery, built on the predictable flash of a dying white dwarf, earned a Nobel Prize and rewrote our fundamental understanding of cosmic destiny. A stellar cataclysm, used as a ruler, revealed that the universe is dominated by a force we cannot see, driving it toward an unknown and lonely future. The predictable flash of a supernova gave us dark energy, but the chaotic aftermath of those explosions gives us something else entirely, a perpetual storm of atomic shrapnel. Supernova remnants are not just beautiful clouds of glowing gas. They are the universe's most powerful and enduring particle accelerators. Long after the initial flash has faded, the expanding shell of debris from the explosion continues to race outward at thousands of kilometers per second. This creates a colossal spherical shock wave, a wall of energy plowing through the thin gas of interstellar space. Within this turbulent frontier, something extraordinary happens to stray protons and atomic nuclei. They become trapped, bouncing back and forth across the shock front like ping-pong balls caught between two rapidly closing walls. With each crossing, the magnetic fields embedded in the shock wave give the particles a powerful kick, boosting their speed. Over months and years, this relentless process can accelerate these subatomic fragments to over 99% the speed of light. When they finally escape the remnant's grip, they become cosmic rays, ultra-high-energy particles that streak across the galaxy. Our planet is constantly bathed in this invisible, energetic rain. Every square centimeter of Earth's upper atmosphere is struck by about one cosmic ray every second. They are the reason for the faint, natural background radiation we live with, and they can even cause random errors in computer memory known as bit flips. To trace this rain back to its source, astronomers look to ancient supernova remnants with perfect laboratory conditions. Take the remnant of SN 1006, a supernova so bright it was recorded across the world. Today, its expanding shell is a perfect spherical bubble in space. Observations in X-ray and gamma-ray light show that the edges of this bubble are glowing with intense synchrotron radiation, the telltale sign of electrons being whipped around by magnetic fields at relativistic speeds. More importantly, we detect a specific high-energy gamma-ray signature coming from the remnant. This light is produced when the protons accelerated by the shock collide with other atoms, a direct fingerprint of the cosmic ray production process in action. By studying SN 1006 and remnants like it, we can measure the efficiency of this natural accelerator. The math is staggering. A single, typical supernova remnant can convert about 10% of the explosion's total energy into accelerating cosmic rays. This means these expanding wrecks are the primary source of the galactic cosmic rays that permeate the Milky Way, a continuous, high-energy particle wind shaped by stellar death. Every time a massive star dies, it leaves behind an engine that churns the galaxy with atomic bullets for tens of thousands of years. These cosmic ray accelerators run for millennia, but the stellar corpses that power them are far from perfectly predictable machines. In the southern sky, within the sprawling, beautiful filaments of the Vela supernova remnant, lies one of the youngest and most active pulsars we know. It spins an incredible 11 times per second, a hyperactive beacon from an explosion that lit up Earth's skies roughly 11,000 years ago. For decades, astronomers have monitored its rhythmic pulse with the precision of atomic clocks, mapping its gradual slowdown as it loses energy. But sometimes this cosmic clock does something utterly inexplicable. It suddenly, without warning, ticks faster. In a fraction of a second, the Vela pulsar's rotation can increase by a tiny but significant amount, a phenomenon astronomers call a glitch. These are not minor hiccups. A single glitch can speed up the pulsar's spin by 1 part in a million, which might sound small, but for an object with the mass of a star compressed into a city, it represents a colossal release of hidden energy. The leading explanation for these sudden jumps delves into the truly alien physics of a neutron star's interior. Picture the outer crust, that rigid lattice of iron nuclei. Beneath it, however, lies a quantum ocean. The incredible density allows a fraction of the star's interior, mostly neutrons, to become a superfluid, a state of matter with zero viscosity that can flow without any friction whatsoever. In this bizarre superfluid, tiny whirlpools called vortices form, and they normally become pinned to the solid crust above. As the pulsar's rotation gradually slows, this superfluid core, isolated by its frictionless nature, wants to keep spinning at its original, faster rate. A tension builds between the slowing crust and the persistent superfluid. Then, without warning, something gives. the pinned vortices suddenly unpin like a dam breaking, and a torrent of this faster spinning superfluid momentum surges outward, transferring its energy to the solid crust in an instant. The entire star experiences a microscopic starquake, and its observable spin jumps. Each glitch is a direct telegram from this impossible realm, offering us our only experimental glimpse into matter compressed to densities greater than an atomic nucleus. It is a place where the rules of quantum mechanics govern objects of stellar mass, and where time itself is kept by a clock that can, without reason, decide to run fast. The spinning clockwork of a pulsar's heart is a realm of quantum extremes, but our own sun's fate is written by a far gentler physics. While massive stars meet their end in cataclysmic blasts that forge black holes and seed galaxies, a star like ours faces a quieter, more poetic dissolution. Our sun will never experience the violent glory of a supernova. Its mass, a steady and stable furnace, is simply too small to trigger that final, apocalyptic collapse. Instead, its destiny unfolds over billions of years in a slow, beautiful fade. In about 5 billion years, having exhausted the hydrogen fuel in its core, the sun will begin its final act. Its core will contract and heat up, while its outer layers will expand outward in a dramatic, cooling swell. Our star will transform into a red giant, its bloated surface engulfing the orbits of Mercury and Venus, and likely rendering Earth a scorched, lifeless cinder. This giant phase is turbulent but not explosive. Eventually, the sun's core will become hot enough to fuse helium into carbon and oxygen, but it will never reach the temperatures needed to fuse carbon into heavier elements. This is the critical limit. Without that next step, the star's core will never build an iron heart. When the helium-2 is spent, the drama concludes. The sun's outer layers, now tenuously held by a fading gravity, will be gently but steadily pushed away by the remaining heat and radiation from the exposed core. This ejected shell of gas will expand into space, illuminated from within by the hot, exposed core. What we will witness from any surviving outer planets is one of the most beautiful sights in the cosmos, a planetary nebula. These glowing, intricate shells of gas, often resembling butterflies or rings, are the final shrouds of sun-like stars. They are not the chaotic debris of an explosion, but a stellar sigh, a slow exhalation that lasts tens of thousands of years. And at the center of that glowing nebula, the sun's core will remain. No longer generating fusion, this incredibly dense, Earth-sized sphere of carbon and oxygen will simply cool over eons, fading from white-hot to red and eventually to a cold, black crystal. This is a white dwarf, the ultimate fate of our sun, a diamond in the dark. Yet even this quiet end holds a latent, spectacular potential. If our sun were not alone, if it were part of a binary star system, its story could have a different final chapter. That white dwarf remnant drifting through space with its companion could begin a slow theft. Over millions of years, it could gravitationally siphon hydrogen-rich material from its neighbor. This stolen gas would accumulate on the white dwarf's surface, increasing its mass. If it ever reached that critical threshold of about 1.4 solar masses, the entire white dwarf would undergo a runaway thermonuclear fusion, detonating completely in a Type 1, a supernova. So while our solitary sun is destined for a gentle fade, its fundamental structure contains the blueprint for the universe's most precise and brilliant bomb, a reminder that even in stillness, the potential for cosmic violence always remains. The quiet fate of our sun leaves no supernova remnant for future astronomers to study. Yet we hold physical evidence of far more violent stellar death right here on Earth, locked inside ancient rocks that fell from the sky. Within primitive meteorites, scientists have discovered microscopic grains of dust older than our solar system itself. These are presolar grains, literal pieces of stardust that formed in the atmospheres of dying stars and survived the chaotic birth of our planetary neighborhood. To find them, researchers dissolve meteorites in strong acid, a process that destroys almost everything except the toughest, most resilient minerals. What remains are tiny crystals, often smaller than a single bacterium, made of silicon carbide, graphite, or even sapphire. Each grain is a time capsule, a messenger from a star that perished billions of years ago. The true story, however, is written in their atomic hearts. Every element comes in different varieties called isotopes, which have the same number of protons but different numbers of neutrons in their nuclei. The exact mix of isotopes created depends entirely on the specific conditions inside a star. When scientists analyze these presolar grains with incredibly sensitive instruments, they find isotopic signatures that are wildly exotic, completely unlike anything found in the material that formed our sun and planets. Some grains contain huge abundances of specific isotopes of silicon or carbon that could only have been produced in the furious helium-burning shells of red giant stars. Others, the most telling, are rich in heavy elements like calcium-44 and titanium-44, which is the decay product of radioactive titanium-44. This isotope has a half-life of only about 60 years. Its presence is a smoking gun. It means the grain condensed from gas that was freshly enriched by a supernova explosion within just a century or two of the blast. Finding this short-lived isotope frozen inside a grain is like finding a photograph with a timestamp from the moment of the star's death. This allows for a breathtaking kind of science, supernova archaeology. By reading these isotopic fingerprints, researchers can do more than just know a supernova happened. They can identify the specific type of star that exploded, estimate its mass, and understand the precise nuclear processes that occurred in its final moments. We are holding, in a laboratory, pieces of individual stars that died long before our sun was even a cloud of gas. These microscopic messengers tell us that the violent deaths of ancient stars did not just contribute a generic soup of elements to our cosmic cradle. They delivered specific, identifiable ingredients, and we can now trace which stellar baker provided which piece of the recipe that eventually became our world. Those microscopic grains are silent witnesses to stellar deaths from a safe distance. But what if the next supernova is not a distant flash but a neighborly catastrophe? The universe's most energetic explosions are not merely spectacles. They are existential threats, and Earth has not always been a safe spectator. Scientists define a cosmic kill zone, a bubble of space within about 25 to 50 light-years of a supernova. Within this range, the event ceases to be an astronomical wonder and becomes a planetary emergency. The initial blast of gamma rays and X-rays is just the opening salvo. More insidious is the prolonged barrage of high-energy cosmic rays that follow, accelerated by the expanding shock wave. This particle radiation would batter our planet's magnetic field and upper atmosphere for centuries. The most devastating effect would be chemical. These energetic particles would smash into atmospheric molecules, triggering a cascade of reactions that would devastate Earth's protective ozone layer. Within a year, global ozone levels could be halved. This fragile shield, which blocks the sun's most harmful ultraviolet radiation, would be stripped away for a decade or more. The result on land and in the shallow oceans would be a biological apocalypse. Ecosystems would collapse under the relentless UV assault, leading to widespread extinctions and potentially triggering a new ice age from atmospheric changes. This is not speculative fiction. The geological record may hold evidence of such a close call. Deep within layers of ocean sediment and on the Moon, scientists have found traces of a rare isotope, iron-60. This radioactive form of iron is not produced naturally on Earth. It is forged only in the heart of a supernova and scattered into space by the explosion. Carefully dated deposits point to a clear signal, a wave of this stellar fallout that washed over our solar system roughly 2.6 million years ago, coinciding with a known period of marine extinctions. The source was likely a supernova or perhaps a series of them occurring within a few hundred light years, close enough to dust our world with the ashes of a dying star. Today, the most famous nearby candidate is the red giant Betelgeuse in Orion's shoulder. It is a ticking bomb destined to explode as a core collapse supernova within the next 100,000 years. Yet at over 600 light-years away, it poses no danger. Its future explosion will be a breathtaking midnight spectacle, visible even in daylight, but its radiation will be too diluted to harm us. The real risk lies in the unknown. While we have catalogued the bright stars nearby, a hidden white dwarf in a binary system could always begin its slow theft, inching toward that thermonuclear limit. The cosmos reminds us that we exist in a fragile balance where the very events that seeded our planet with life could, from a slightly different vantage point, just as easily erase it. That radioactive iron in our seabed is a whisper from a distant, ancient death, but we have a far louder, far closer reminder that the cosmos is alive with impending violence. Hanging in the constellation Orion, the star Betelgeuse is a ticking time bomb. This is not a metaphor. Betelgeuse is a red supergiant, a star in the final, unstable chapter of its life. It is so colossal that if placed at the center of our solar system, its surface would extend past the orbit of Jupiter, engulfing the inner planets, and it is dying. Astronomers classify it as a prime candidate for a core collapse supernova, an event that could happen tomorrow or 100,000 years from now. What makes Betelgeuse so captivating is that we can watch its death throes in real time. In late 2019 and early 2020, the star did something extraordinary. It dimmed dramatically, losing nearly 2/3 of its usual brightness. This great dimming event sent astronomers scrambling. Was this the final act? The subsequent investigation revealed a cosmic sneeze, not a death rattle. Observations from the Hubble Space Telescope and other instruments showed that the star had likely ejected a massive plume of superheated gas. As this material cooled, it condensed into vast clouds of stardust, partially blocking Betelgeuse's light from our view. It was a spectacular stellar burp, a preview of the titanic mass loss that precedes the final collapse. When Betelgeuse does finally exhaust the fuel in its core, its end will be a landmark event in human history. The explosion will be unmistakable. For a few weeks, a new, piercing point of light will appear in Orion. It will not twinkle like a star. It will shine with a steady, fierce intensity, potentially rivaling the brightness of a full moon. Imagine a second moon, but concentrated into a single, brilliant pinprick. It would be visible in broad daylight, casting faint shadows at night. This celestial beacon would remain visible to the naked eye for several months before gradually fading, leaving behind a new nebula that would grow and change over centuries. Beyond the spectacle, the scientific value would be immeasurable. For the first time, we would have a front-row seat to the death of a star whose entire life cycle we have studied in detail. Our neutrino detectors would be flooded with trillions of those ghostly particles, giving us an unprecedented scan of a supernova's engine. Every telescope, from radio to gamma ray, would be trained on it, capturing the birth of a neutron star or a black hole in ultra-high definition. We would watch the shockwave plow into previously ejected material, lighting up the complex surroundings of the star's final years. Betelgeuse's supernova would be more than a show. It would be the ultimate masterclass in stellar evolution, a chance to test every theory against the brilliant, unforgiving light of reality. Betelgeuse will one day flood our sky with light, but its final contribution will be a legacy of chaos and creation. The expanding shell of its supernova remnant will not simply drift into emptiness. It will become a cosmic sculptor, reshaping the very fabric of our galaxy. Supernova remnants are the primary architects of the interstellar medium, the thin soup of gas and dust that fills the space between stars. This is not a gentle process. It is a continuous cycle of destruction and rebirth on a galactic scale. when a remnant shockwave, still moving at thousands of kilometers per second, slams into a cold, quiet cloud of interstellar hydrogen, it delivers a titanic impact. The cloud is violently compressed, its atoms squeezed together. In some regions, this sudden increase in density overcomes the cloud's internal pressure, causing pockets to collapse under their own gravity. These collapsing knots are the seeds of new stars. The shockwave, in essence, gives the cloud a powerful kick, initiating a wave of stellar birth along its leading edge. We see this directly in our own galaxy, where the ragged edges of supernova remnants are often bordered by clusters of bright, young, blue stars, all born from the turmoil of a prior stellar death. But the shockwave's work is only half the story. As the remnant expands for tens of thousands of years, it does more than push material around, it heats it. The interior of the remnant becomes a vast million-degree bubble of extremely thin, ionized gas. This hot plasma is so energetic it can blow a hole straight through the cooler layers of the galactic disk, creating colossal cavities. Our own solar system floats inside one such structure right now. It is called the local bubble, a region of space roughly 1,000 light-years across where the interstellar medium is far hotter and more diffuse than the galactic average. We are not at the center, but sailing through it. This bubble was not carved by a single explosion. The best evidence suggests it was the work of perhaps 15 to 20 supernovae that occurred in a nearby star cluster over the last 10 to 20 million years. Their successive shockwaves merged, sweeping up cooler gas and dust into a dense shell that now surrounds us like the wall of a cosmic cavern. Inside this bubble, the environment is strangely quiet. The hot, thin gas offers little resistance, allowing our sun and neighboring stars to move through it with ease. It is a stunning realization. We live inside a fossil, a monument to a series of ancient cataclysms that cleared our celestial neighborhood and whose fading echoes still define the space through which our planet travels. The supernova's role is never just an end. It is a violent, necessary reset button for the galaxy, ensuring that the ashes of dead stars become the nurseries for the next generation. This fundamental mass threshold is a rule written into the fabric of the cosmos, a boundary that defines life and death for a stellar corpse. It is called the Chandrasekhar limit, named for the brilliant astrophysicist Subrahmanyan Chandrasekhar, and it is set at about 1.4 times the mass of our Sun. This number is not arbitrary. It represents the ultimate victory of quantum physics over the crushing force of gravity. A white dwarf is a sphere of carbon and oxygen, the ashes of a star's final burning. It is supported not by nuclear fusion, but by a quantum mechanical principle called electron degeneracy pressure. The electrons within the star, packed together unimaginably tightly, resist being squeezed any further. They push back against gravity's relentless pull. Chandrasekhar's calculations revealed a terrifying truth. This electron pressure has a maximum strength. If the total mass of the white dwarf exceeds that 1.4 solar mass limit, gravity wins. The pressure fails and the star collapses catastrophically. For an isolated white dwarf like the one our Sun will become, this limit is never reached. It simply cools in peace. But place that white dwarf in a binary dance with a living star and the story changes. Through a slow, gravitational theft, the white dwarf can siphon hydrogen-rich material from its companion. This stolen gas piles onto its surface, increasing its mass atom by atom over millions of years. It is a patient countdown to oblivion. The moment the white dwarf's mass ticks past the Chandrasekhar limit, everything changes in an instant. Gravity overwhelms the quantum support. The core is compressed and heated to unbelievable temperatures, triggering the fusion of carbon in a runaway thermonuclear chain reaction. There is no shockwave to blow the star apart from the inside out. Instead, the entire white dwarf, from its center to its surface, becomes fuel. In less than a second, the stellar corpse is completely incinerated, vaporized in a flash of light so uniform and so brilliant it can be seen across the universe. This is the Type 1, a supernova, the cosmic standard candle. Its predictability stems directly from this precise mass threshold. Every white dwarf that explodes in this way does so at nearly the same mass with nearly the same internal composition, leading to nearly the same peak brightness. The Chandrasekhar limit is the universe's quality control, ensuring that these stellar detonations are so consistent we can use them to measure the expansion of space itself. It is a simple number that governs one of the most complex and useful explosions in the cosmos. That precise limit governs a white dwarf's fate, but the death of a massive star is a far messier and more chaotic affair. The universe's most powerful explosions are rarely symmetrical. In fact, the beautiful, round supernova remnants we often see in photographs are an illusion of time and scale. The initial blast itself is almost never a perfect sphere. This fundamental asymmetry is written into the violent physics of a core collapse supernova, and we have the evidence to prove it. Look at the remnant of Cassiopeia A, the debris from a star that exploded around the year 1680. This cosmic wreckage is not a serene, expanding bubble. It is a tangled, chaotic knot of filaments and shrapnel. Fast-moving knots of silicon and iron are blasted in one direction, while slower-moving debris expands elsewhere. It looks less like an inflated balloon and more like a hand grenade went off inside a junkyard. This lopsided structure tells a clear story. The explosion that created it was profoundly off-center, punching material out in preferred directions with unimaginable force. But how do we know this asymmetry starts at the very heart of the explosion? The light itself holds the secret. When astronomers study the light from distant supernova, they can measure its polarization. Ordinary light waves vibrate in all directions, but if that light scatters through an asymmetrical cloud of debris, it becomes polarized, meaning the waves align in a preferred direction. This is exactly what we see in many core collapse supernova. The light is polarized, sometimes strongly. This tells us the expanding cloud of gas is not a smooth sphere. It is shaped more like a rugby ball or even a distorted peanut, with one axis longer than the other. The explosion had a definite direction, a preferred axis of violence. So what causes this stellar imbalance? The culprit lies in the neutrino-driven engine at the star's collapsing core. For decades, simulations struggled to make a star explode symmetrically. The standing accretion shock instability, or SRSI, is a key player. As the shockwave stalls after the initial core bounce, it begins to wobble and slosh like water in a tilted bucket. This sloshing motion breaks spherical symmetry, creating large-scale oscillations that can help revive the stalled shock and push the explosion in one direction over another. In some of the most massive stars, the collapse leads directly to a black hole and the formation of ultra-powerful jets. These jets, like cosmic blowtorches, drill through the star and eject material preferentially along their axis, creating an explosion that is intrinsically bipolar, like two opposing cannon shots. This inherent lopsidedness has a dramatic consequence for the stellar corpse left behind. That neutron star or black hole does not just sit quietly at the center of the remnant. It receives a powerful kick. Think of it as the recoil from an unbalanced gun. If more mass and energy are ejected in one direction, the conservation of momentum demands that the dense remnant rockets off in the opposite direction. These kicks are not gentle. A newborn neutron star can be launched at speeds exceeding 5 million miles per hour. At that velocity, it can easily escape the gravitational pull of its own supernova remnant and even its home galaxy, becoming a hypervelocity rogue star destined to wander the interstellar void alone. We have observed these cosmic cannonballs, neutron stars racing through space with vast, elongated wakes of shocked material trailing behind them. Their tremendous speed is a direct echo of the asymmetric cataclysm that gave them birth. Every lopsided remnant and every runaway pulsar confirms a profound truth. The universe's most energetic explosions are not tidy, spherical events. They are chaotic, directional, and fundamentally messy, imparting a violent spin and a staggering velocity to the strange new objects they create. These runaway pulsars are the shrapnel from lopsided blasts, but not every stellar death leaves a clear signature. A new and baffling class of cosmic explosion is forcing astronomers to rewrite the rulebook entirely. They are called fast blue optical transients, or FBOTS, and they defy every expectation. The most famous example is an event nicknamed the Cow, discovered in 2018. At first glance, it looked like a supernova in a distant galaxy, but within days it became clear this was something entirely alien. The Cow did everything too fast. It brightened to peak luminosity in under 2 days, while a normal supernova takes weeks. It then faded away just as rapidly, its blue optical light vanishing almost as quickly as it appeared. This was not a slow, lingering death. It was a sudden, brilliant flash, like a cosmic camera strobe. The temperature was another clue. The Cow was scorchingly hot, reaching around 27,000 degrees Celsius at its peak, far hotter than the expanding, cooling gas of a typical supernova. And perhaps most intriguingly, it showed signs of a powerful central engine, emitting a steady stream of X-rays long after the initial optical flash had faded. This suggested something was still active, still pouring energy into the debris from within. So what could possibly cause such a bizarre, fast and hot event? The leading theories are as dramatic as the phenomenon itself. One idea is that we are witnessing a failed supernova, the direct birth cry of a black hole. In this scenario, a very massive star collapses, but its outer layers fall back onto the core so quickly and completely that a traditional supernova shockwave never successfully breaks out. Instead, the newborn black hole immediately begins devouring the infalling stellar material. As this matter swirls into the abyss, it forms a brief, incredibly hot accretion disk that shines with intense blue light before being swallowed, resulting in that rapid rise and fall. Another possibility is even more violent. Perhaps an FBOT is a star being shredded not from the inside but from the outside. This would be a tidal disruption event, but with a twist. A star wanders too close to an intermediate mass black hole. The black hole's gravity stretches and tears the star apart in a process called spaghettification. As the stellar debris rains down, it could form a short-lived, ultra-hot disk of matter that produces that characteristic fast blue flash. Or, in a binary system, a black hole might collide directly with a star, creating a similar cataclysm. These mysterious flashes represent the frontier of explosive astrophysics. Each new detection challenges our categories, reminding us that for every rule we think we understand about stellar death, the cosmos has a spectacular exception waiting in the dark. The chaotic flashes of FBOTS challenge our categories, yet the most profound impact of a supernova is not its momentary brilliance, but its enduring creative legacy. These explosions do far more than forge heavy metals. They are the cosmic catalysts for life itself. The initial blast synthesizes the raw atomic ingredients, but the expanding shockwave that follows performs an even more delicate alchemy. As this wall of energy, moving at thousands of kilometers per second, plows into a cold, dark molecular cloud, it delivers more than just a compressive shove. It delivers a spark. The tremendous heat and pressure from the shock can trigger chemical reactions in the cloud's icy dust grains, transforming simple atoms and molecules into complex organic compounds. Laboratory experiments simulating these conditions have shown that such shocks can synthesize molecules like formaldehyde, hydrogen cyanide, and even the precursors to amino acids, the very building blocks of proteins. It is a stunning realization. The same violent event that obliterates a star also acts as a cosmic chemistry set, jump-starting the formation of the molecular machinery necessary for biology in the stellar nurseries of the next generation. This process is not a one-time event. It is a cycle written into the history of our galaxy. the first stars composed only of hydrogen and helium, lived fast and died in supernova that polluted the pristine cosmos with the first heavy elements. Those elements mixed into interstellar clouds allowed second-generation stars to form with rocky planets. Those stars, in turn, lived and died, their supernova enriching the clouds further with more diverse chemistry. Each stellar death added another layer of complexity to the galactic reservoir. Our own solar system formed from a cloud that had been seeded by countless such explosions over billions of years. This means the iron in our blood, the carbon in our DNA, the phosphorus in our bones, and the nitrogen in our air are all gifts from long-dead stars. But the supernova did more than just donate the atoms. They created the rich, chemically diverse environment where those atoms could link together into ever more complex structures. The shockwaves provided the energy for the first steps up the ladder of chemical complexity. Without this continuous cycle of stellar death and rebirth, the universe would remain a barren place of simple gases, incapable of forming a single rocky world, let alone the intricate chemistry of a living cell. We are not just made of stardust, we are the product of a cosmic inheritance funded by the most energetic explosions in the universe. The atoms in our bodies are a testament to this ancient creative violence. But to truly understand the moment of their birth, we must step inside the explosion itself. This is not possible with telescopes alone, so scientists have built digital stars in some of the world's most powerful supercomputers. Their goal is to answer a deceptively simple question: what exactly makes a star blow itself apart? Simulating a core collapse supernova is one of the most daunting challenges in all of computational physics. You are not modeling a simple sphere of gas. You are attempting to recreate in 3 dimensions the chaotic final second of a star's life, where extremes of gravity, nuclear physics, and particle behavior collide. The simulation must track the collapse of an iron core the size of Earth, rebounding into a shockwave that then stalls, only to be revived by a flood of ghostly neutrinos. It must account for the turbulent convection sloshing beneath the shock, the potential growth of deadly instabilities, and the possible role of the star's own rotation and magnetic fields. Every one of these elements interacts with the others in a ferocious feedback loop. To capture this complexity, researchers divide the virtual star into hundreds of millions, sometimes billions, of individual cells, each with its own properties like density, temperature, and velocity. The equations governing the behavior of matter and energy in each cell must be solved over and over again for tiny fractions of a second to see how the entire system evolves. This computational burden is staggering. A single, high-resolution, 3-dimensional simulation of the first second after core bounce can consume millions of CPU hours on a supercomputer. That is the equivalent of running a powerful desktop computer continuously for centuries. These digital laboratories have revealed why stars explode. For decades, one-dimensional models failed. The shockwave would stall every time, leading to a quiet collapse into a black hole, not an explosion. The breakthrough came with 3-dimensional simulations that fully incorporated the intricate dance of neutrinos and fluid motion. They showed that as neutrinos pour out from the newborn neutron star, they heat the material just behind the stalled shock in an uneven way. This creates powerful bubbles of rising hot plasma and sinking cooler matter like water boiling in a pot. This violent churning, combined with the sloshing from the standing accretion shock instability, helps push the shock outward in a lopsided manner, finally reviving it and driving the explosion. The simulations do not always succeed. Small changes in the star's initial mass, rotation, or composition can lead to a failed supernova and a direct collapse to a black hole. This virtual experimentation is why we can look at the messy remnant of Cassiopeia and understand its asymmetry. It tells us which stars are likely to explode and which will vanish silently. Every time we observe a supernova's light curve or measure its elemental debris, We are seeing the real-world echo of these monumental digital experiments, where the universe's most violent seconds are painstakingly rebuilt inside a machine. For millennia, the night sky was considered a perfect and unchanging tapestry. Then, without warning, a new star would blaze into existence, visible for weeks or months before fading back into the void. These were not distant curiosities for ancient astronomers. They were profound cosmic disruptions witnessed by human eyes and etched into our historical records. One of the most spectacular was the supernova of the year 1006. Appearing in the constellation Lupus, it was recorded by observers from China to Egypt to Europe. The Egyptian scholar Ali ibn Ridwan described it as a large circular body, 1/3 the size of the moon, that shone with a brilliance that cast faint shadows. Modern calculations suggest it may have been the brightest stellar event ever witnessed, perhaps rivaling the crescent moon in intensity. This was not a subtle portent. It was a celestial conflagration impossible to ignore. Its light reached Earth in the spring of 1006, and for months it dominated the night, a stark challenge to the philosophical idea of celestial perfection. Then in 1054, another guest star, as Chinese astronomers called it, appeared in Taurus. This was the supernova that created the Crab Nebula. Court astrologers of the Song dynasty meticulously documented its position, noting it was visible in daylight for 23 days and remained naked eye visible at night for nearly 2 years. Their records were so precise that modern astronomers could pinpoint the exact remnant. These events were more than omens. They were data points, accidental experiments in cosmic observation that would resonate centuries later. The shock to the old world view became even more direct in 1572, when a brilliant new star shone in Cassiopeia. The great Danish astronomer Tycho Brahe did more than just note its presence. He meticulously measured its position night after night with his revolutionary instruments. He proved conclusively that it displayed no parallax, meaning it was far beyond the moon, in the realm of the so-called fixed stars. This was a fatal blow to the Aristotelian doctrine that the heavens beyond our moon were immutable and perfect. If a new star could appear and fade in the distant firmament, then the cosmos was capable of change. Just 32 years later, in 1604, Johannes Kepler observed another supernova in Ophiuchus. His detailed study, following Tycho's example, further cemented this revolutionary truth. The heavens were not a static backdrop. They were a dynamic, evolving arena where stars could be born and could die in spectacular fashion. These historical supernovae did more than light up the medieval sky. They lit the fuse for a scientific revolution. By demonstrating that the distant cosmos could change, they shattered a 2,000-year-old dogma and opened the human mind to a new, more vibrant and violent universe. Those historical supernovae shattered our view of a static sky, but the next revolution will reveal a cosmos alive with invisible violence. We stand on the brink of a new era in explosion astronomy, where a suite of next-generation observatories will transform whispers into roars and shadows into brilliant clarity. The coming decade will be defined by machines that see everything, hear everything, and dissect the light of creation itself. First, the Vera C. Rubin Observatory, currently under construction in Chile, will conduct a relentless 10-year survey of the entire southern sky. Its enormous mirror and gargantuan camera will scan the heavens every few nights, not to take pretty pictures but to detect change. It will catch the birth of supernovae in their very first hours, track the fading glow of kilonovae, and discover thousands of bizarre, fast transients like the cow that current telescopes simply miss. It will provide the ultimate inventory of cosmic violence, a real-time movie of the dynamic universe. But to understand what these flashes mean, we need to look deeper. The James Webb Space Telescope is our ultimate chemical analyst. Its infrared eyes can peer through the dust shrouding stellar nurseries and supernova remnants, directly analyzing the light from these events to identify molecules and elements. It could watch the formation of complex organic compounds in the shockwaves of a remnant, or measure the precise isotopic ratios in a kilonova's glow, telling us exactly how much gold was forged in a single collision. Yet light is only part of the story. The future also belongs to sound. The Laser Interferometer Space Antenna, or LISA, is a revolutionary mission that will place 3 spacecraft in orbit, forming a gravitational wave observatory millions of kilometers in size. While ground-based detectors like LIGO hear the high-frequency chirps, LISA will listen to the low-frequency hum of the cosmos, detecting the final spirals of supermassive black hole mergers and the gentle, persistent ripples from white dwarfs orbiting for millions of years. It will give us a soundtrack to the universe's most violent choreography. Together, these new eyes and ears will transform our understanding. We will not just see explosions. We will witness their chemical aftermath, feel their gravitational tremors, and catch them in the act of being born. We will move from studying individual events to understanding the grand, interconnected cycle of stellar life and death across cosmic time. The final frontier is not a place, but a new way of perceiving the universe itself in all its violent, creative, and symphonic glory. This incredible journey through cosmic cataclysm reveals a universe of breathtaking duality. From the quiet death of a sun-like star to the hypernova that births a black hole, these explosions are the universe's fundamental engines of change. They are endings of unimaginable violence, yet from that violence springs all creation. The iron in our blood, the gold in our jewelry, the very air we breathe, were all forged in these stellar furnaces and scattered by their shockwaves. They are the cosmic recyclers, taking the ashes of dead stars and using them to build new worlds, to trigger the birth of suns, and to enrich the galactic ecosystem with the complex chemistry that makes life possible. They are also the universe's most precise tools, their predictable flashes allowing us to measure the accelerating expansion of space itself. These events remind us that we are not separate from the cosmos. We are a product of its most energetic processes. The next time you look up at the night sky, remember that the darkness between the stars is not empty. It is a graveyard and a nursery filled with the echoes of ancient detonations and the seeds of futures yet to come. Every point of light has a story that ends in cataclysm or a quiet fade, and each ending is a beginning somewhere else. If you found this voyage into the heart of stellar violence fascinating, consider subscribing. We have only scratched the surface of the cosmos's deepest mysteries, and there are countless more wonders waiting to be explored.